Thanks for the introduction and thanks for attending my talk. So this is the program verification session, and that's also the application of symbolic execution that I have in mind. So the general setting may be something like this. Given an implementation, we want to derive if it's conforming to its specification, for instance, giving us pre and post conditions. And if you're somewhat formally about it, if you're serious about it, you might want to do it somewhat formally, and if you're very serious, you might actually want to mechanize it in a proof assistant. So the general approach, or the common approach, is something like this. We embed the syntax of our language deeply in the proof assistant, just representing the AST as a data type. But for the assertions, we use a shallow embedding. So meaning we represent assertions somehow using the propositions of the system. We then use the facilities that the proof assistant gives us, for instance, to do simplifications and to use reasoning rules of our logic. And the system will check that each step is actually sound. So that means that our program verifier is essentially a meta program, and each run of this meta program is verified to be sound individually. What if we actually used a deep embedding for assertions as well? And instead of implementing a meta program, we implement just a normal program in the proof assistant. So that means that, with the goal of also proving soundness, but proving soundness once and for all for every run instead of for each individual run. So this is what this talk is about. It's a systematic approach of how to use symbolic execution to actually build such program verifiers, which are semi-automatic. So in general, we might be in a case where it's undecidable. So we need some help from a user to actually perform certain verifications. The other contribution that I also want to talk briefly about is Catamaran. So this is a program verifier that we are building for the SAIL language, which is a specification language for instruction sets. The structure so that we are proposing is as follows. So essentially, you build the system twice. Once you implement a symbolic executor, as I said, which works with deep embeddings, and you also implement a shallow executor, which has the same structure, has the same behavior to a certain extent, but uses shallow embeddings. And we want to make this this proof. So we want to reduce the soundness proof of our symbolic executor to the shallow executor, and we want to make this soundness proof as systematic and as, well, hopefully pain-free as possible. Once you're in the shallow world, you're kind of like in familiar waters, and you can just use the normal techniques, for instance, to show that this yields a valid derivation in the program logic. Or whatever you want. So for Catamaran specifically, we also specified an axiomatic program logic. We proved the shallow executor sound with respect to that one. We instantiated the iris framework with the operational semantics of our language, and we proved that the axioms of the program logic hold in the iris model. So for this talk, I will be talking both about shallow and symbolic execution, and I will use some color codes. So in purple, this will all be the symbolic executions, and in turquoise, that will be the shallow one. I will also use capitalized and not capitalized letters, so just that you don't lose the orientation. So let's start with the shallow execution first. Pre and post conditions, so hard triples are a bit clunky, so I want to change the setting a bit. So in general, I want to talk about verification conditions, which are just a formula which are sufficient to actually prove a derivation in the program logic. But more specifically, I really want to talk about weakest preconditions, so which may be one way to implement a verification condition generator in a, well, traditional naive way. If we look at the type of the weakest precondition operator, for instance, applied to some statement of an imperative language, it maps predicates on outputs to predicates on inputs, right? It maps a post condition to a precondition and a weakest precondition. In a proof assistant, we might actually want to take predicates to be just mappings to the propositional types, so just X to prop. If we use this definition, we can shuffle the type around a bit, and we have a mapping that goes from the input to cont prop output, so to the continuation monad with answer type prop and result type output. So this is also called the backwards predicate transformer monad. You might have seen this already. So in the past, there has been a flurry of research papers that are advertising Dijkstra monads, and they are promising us to give them to us for free, for all and forever. So the general idea is that you actually use these monads to write your specifications in, and if you also implement a monad morphism from your computations to the specification monad, you can derive a verification condition generator. And you can use that to reason about monadic code. So that's very common in the F-star system, where also like a lot of the authors work on. So what if our monadic code is actually a monadic interpreter for an object language? I mean, just what we did previously. That means that this interpreter basically implements the semantics of our object language as the weakest predicate transformer, and we can use that to implement a verification condition generator. If you want to add side effects to your interpreter, that's fine. So you can just use monad transformers like state exception, non-determinism, and it will give you a transformed continuation monad which has the right shape of postconditions. Okay, let's do this. So let's maybe interpret an expression language and derive something that computes a value in such a monad. So if we look at the if case, we want to evaluate the condition first, and then depending if it's true or false, use one of the branches. So here I'm implementing the object level if using the meta level if, which means I'm using pattern matching. We have to think a bit ahead, so we want to also implement the symbolic executor, in which what should that one do in this case. So we can somehow represent pattern matches also explicitly, or we can go a traditional route again and avoid pattern matches and translate them away. So there are reasoning rules for weakest preconditions, which use the logical connectives of your assertion language to kind of like implement these. We can abstract away from this a bit. So these features, if we really want to work at the level of abstraction of the monad, correspond to actually angelic and demonic non-determinism features. So we can implement angelic non-determinism with the underlying exist quantifier, demonic with the for all, binary non-determinism using disjunction and conjunction, and then we can also implement guards, for instance, that a certain proposition has to hold, or that we can assume a certain proposition for the remainder of an execution path. So if we use this, then the pattern match is gone, and this seems to be something that we might also be able to implement in the symbolic setting. Just to note here, the control flow constraints that are assumed are equalities, which will be generally the case for almost every language. Okay, let's look at the symbolic executor. Let's talk about kind of like what we want to represent first. So the propositions that we want to deeply embed instead of the shallowly embedded propositions. So symbolic values, we're using existential and universal quantification. We have to represent them somehow. So we are defining a set of logic variables, and then we're also defining a set of symbolic values or symbolic expressions, which have all the formers of values, but also have a new case for the symbolic variable. The constraints, the control flow constraints specifically, as I said, are equations between symbolic expressions, but we can also add here user-defined theories, so for instance, that come from the pre and post conditions, which are then in a user-defined subset, which can really be anything. For the symbolic propositions, so we have to implement something that actually allows us to define the angelic and demonic non-determinism features. So we just provide versions of the logical connectives that we used here as constructors. So the idea is now use a monad that actually uses this symbolic representation as an answer type and implement weakest preconditions using that, and implement the symbolic verification condition generator using that. So there are some challenges, right? So now all of a sudden we have to deal with variable binding ourselves, so we have to ensure that all of the propositions that we generate are actually well scoped and well formed and well typed. And we have to reason about this, right? Fortunately, we already have the machinery to actually do that. So this is very similar to the case of dynamic allocation of memory, so for which we use possible wealth semantics, which also we can also use in this case to reason about the logic variables. There's another challenge, and that is combinatorial explosion, so just exponential explosion because of a more or less naive implementation of the weakest pre. So what do symbolic executors, so like, I mean, realistic systems do? They try to do a lot, actually, to like avoid really an explosion of execution paths. So they might want to, for instance, detect when a certain assertion is actually unsatisfiable. So for instance, here false equals true. And in this case, we have in the second component here of the conjunction, we have a whole subtree which we would need to compute, which of course we will just throw away in the end. So when we already detect this unsatisfiable constraint, we just want to abort the symbolic execution and just put a false there. So not only do we want to do that locally, but we actually want to keep track of all the past control flows constraints that we've seen, and maybe also restrictions or constraints that come from the precondition or from postconditions of called functions and so on. So how can we actually incorporate that also in kind of like our program and in our reasoning? So let's maybe look at a quick example. So here's a nested case where we pattern match on the same variable twice. So that means that one of the execution branches is, of course, impossible. So this can't be a talk about symbolic execution without a tree. So here's the tree. So each node here in the tree corresponds to a control flow point in the program. And as you can see in the middle, there's the point where we want to be the in left of where X is and then in left and in the other one, in left and in right at the same time, which is of course inconsistent. So people in symbolic execution, they not only represent the program state, but also contextual information, so the control flow constraints from a node to the root of the tree and all the logic variables that have been introduced. So what if we just took these constraints and put them in our worlds as well? So we use possible world semantics to represent the binding and keeping track of logic variables, and we also use it to keep track of the constraints. So we define worlds like that, and accessibility basically means, okay, we can just add more constraints and more variables, but we can never take anything out. So how do we actually program this? We can, so in order to do that, we need to keep somehow track of these worlds. So it would be best kind of like if we could actually abstract away from this, and I will show you how we can define some of the type formers that will more or less hide a bit of the details. But essentially, we will keep just parsing worlds to subcomputations and dealing with them explicitly. Furthermore, we will not only parse them in our implementation, we also index everything that comes after by the worlds. So we work with families of world index types. And we do that to make sure that, well, all of our propositions and all of our symbolic values are well scoped and well typed, which other people have done before. But we also make sure that the constraints are consistently used. So you can never move a value which was generated under a certain constraint, for instance, to a sibling in the execution path or to a parent in the execution path, in the execution tree, sorry, because that would be unsound. So for the type formers, we can define a form of function types. So add world W, this is just a function of the corresponding indices, family members. So we go here a modal logic route. So we define an explicit box operator, which makes sure that a type or specifically functions are monotone, which we do by just universally quantifying over an accessible world. So specifically, what we want, what we've seen here previously, we have 3 leaves or 3 subtrees in which we use the post condition, right, on E1, E2, and E3. So these are in different worlds, but at the very beginning, at the top of this execution tree, the post condition was, well, in a single world. So we define the predicate transformer monad actually with a box post condition, so that we're sure that post conditions are actually monotone. So for the programming, we can define all of the abstractions, so assume, assert, guards, and so on, using these primitives. So there's a bit of world passing here. Actually, it's as accessibility witnesses that we're passing, but otherwise the program really has the same structure. For pruning unreachable states, so in some of the primitives we can actually do more, right? Because we have access to the world. So for instance, in the assert, we might take the current world, the formula that we are asserting, and run a solver which will tell us, yes, that formula, well, is valid or is derivable or is inconsistent with the constraints that we've seen previously. So we could completely prune this execution path here at this point. So for the soundness, I will actually skip this. So the keyword here is to define a Kripke index logical relation that actually links the 2 implementations. So it's very much like an equivalence proof, just that, well, instead of an equivalence, you want to show that the symbolic computation is actually stronger than the shallow one. For our implementation catamaran, as I previously said, it's a separation logic verifier implemented in Coq. It's not fully automatic, it's semi-automatic, and we also have some escape hatches, so we don't do everything using catamaran. It's mostly there to really get rid of very boring boilerplate where you just want to apply very basic rules, very basic cancellation, and so on. For the very hard and interesting cases, these we actually do manually in the Iris framework. So as I said, it's semi-automatic. That means we allow the user to, well, provide some automation himself. So the whole system is parameterized by user theory, and he can also provide a solver himself. We have a generic solver for some of the background theory. You can implement some reasoning steps using ghost statements in the code, and then at the end, we might even generate a verification condition, which has residual proof obligations, which we still have to prove. Just as an example, for separation logic case, which has been implemented in some other systems, are Reynolds heap allocated linked lists, so mutable data structures. So we've tested that the verification times in VST in the separation logic foundations in Bedrock, for which you will find the numbers only in the paper. So here are the results. As you can see, for the verification times, catamaran is 1 to 2 orders of magnitude faster, which is consistent kind of like with other observations where computational reflection speeds up proofs with this magnitude. If they're missing bars, that means that, well, we couldn't actually find an implementation in the code base of these systems. There are also lemmas that we have to prove, for instance, the folding and unfolding of the linked lists and the user theory. So that takes a bit of time, more time to do in catamaran because of the symbolic representation. So in the paper, you will find some more information about symbolic heap separation logic, about adding debug information, and about another case study, which is a bit larger. So in conclusion, we use possible world semantics to reason about logic variables and the constraint in symbolic execution. We can reduce the soundness of symbolic execution to shallow execution, and we get a program verifier with competitive performance. Thank you for your attention.